Well, this is it, the end of the road, the last lecture of the course. All good things must come to an end and all that. But before we go, for old time's sake, let's take a look at one more algorithm problem. It's pretty straightforward. It's a little bit of a puzzle to solve. So I'm going to provide you with a collection of blocks. There they are. Notice that each block contains a string on the top and a string on the bottom. And your task, the goal of this algorithm problem, is to decide whether it is possible to create some sequence of blocks, and you're allowed to use a particular block as many times as you want, whether it's possible to create some sequence of blocks such that if I read off the complete string that I create by combining together the top row of every block, I get the same string as I would if I read off the bottom row of every block. So I'll give an example. For this particular collection of blocks, it turns out that I am able to do that. So for example, if I choose this sequence here, notice that if I read off the complete string from the top row, I get the word raspberry. And if I read off the complete string from the bottom row, I get the word raspberry as well. So as far as the decision problem we are trying to solve, in this case, the answer is yes. I can take some of the blocks, I can put them together in an order such that I get the same string on the top and bottom. All right, how about this sequence of blocks? You can go right ahead and pause the video while you try to puzzle it out yourself. Okay, I'll assume that you've done that. It turns out that for this sequence of blocks, the answer is also yes. I can arrange the blocks like this, and I get the string mathematics on the top and the string mathematics on the bottom. And this example also illustrates an important characteristic of this problem. I'm not just looking for some permutation of the blocks or some subset of the blocks. I'm allowed to make as many copies of each block as I want. You'll notice that the block M over MA gets used more than once. And actually the block A over T gets used more than once as well. In general, I can use each block as many times as I want. I could end up with a sequence that is far, far longer than the number of blocks I was originally provided because of all the duplicates that I'm using. Okay, what about this sequence of blocks? Is there a way of choosing some sequence of this sequence of blocks such that I get the same string on the top as on the bottom? Okay, I'll let you think about it. Turns out that the answer is no. Now, I can justify why the answer sort of has to be no here. Notice that there are no blocks that have a shorter string on the top than they do on the bottom. Now, that's not inherently a problem. In this particular case, it does allow us to rule a bunch of blocks out. So because none of the blocks have a shorter string on the top, I can never use any of these blocks. Because if I use them, they're going to make the total string on the bottom too short. They're going to mean that the total string on the top ends up a little bit longer than the one on the bottom, and there's no way to fix that, because the only way to fix that would be to use a block where the string on the bottom is longer. Okay, so I can't use any of these three blocks. Or actually, I can't use this block either. Okay, now notice that if I use these other blocks that I've been left with, so AB over BA and PB over BR, okay, well, there is no way that I could use PB over ER because that would result in there being an R on the bottom. And there is no way of getting an R on the top with the blocks that I'm still allowed to use. Okay, so I'm just going to clean up my work here a little bit. So that means this block is out of the question. And I also can't get what I want using only copies of this block here. Although I have the right letters, there's no way to put them in the right order. There's certainly no number of repetitions of this block that will give me what I want. Okay, so in this case, I can conclude that the answer is no. There is no way, there is no sequence I can construct of this set of blocks, even if I can use as many of them as I want, that's going to give me the same string on the top as on the bottom. Also notice that for this particular input sequence, I was able to rule out any possibility, so I was able to say that the answer was no by a fairly straightforward deductive process. I just kept ruling out certain blocks until it became clear that no blocks could really help me. In the previous case, I was able to demonstrate that the answer was yes by means of what we now know is called a certificate. If I want to prove to you that the answer is yes, I just have to provide you a sequence of blocks. Okay, so I would say that all of that taken together does sort of put this problem in our wheelhouse. It does sound like a lot of the problems that we were talking about theoretically last time, and moreover, I don't know that it looks very complicated. Now, we've been burned in that sense before. I mean, we didn't think the partition problem was very complicated, and it turned out it was rather difficult. But it seems, at least superficially, that we have tackled problems that are a great deal more difficult than this. Okay, well, we'll wait and see about that point. Okay, so we could frame this thing as a decision problem, and this decision problem has a name. Now, of course, that's never a good sign. That means there's something significant about it. This problem is called the post-correspondence problem, and the word post here is because it was named after somebody named Post. And I will frame it like this. Suppose you are given a collection of n blocks, and we'll just call the blocks bi. Now, each block is actually a pair of two strings. We'll call the top string xi and the bottom string yi. And it's just a decision problem. Although a certificate might be helpful, all you really have to produce to solve this problem is a yes or no answer. Prove that some algorithm can produce the correct answer in all cases. So the answer is yes, if there exists some sequence of indices, that is to say, some collection of indices for blocks, such that if I concatenate together the top string for that a sequence of blocks, I get the same thing as if I concatenate together the bottom string. So the answer is true if that's the case, and false otherwise. So a fairly straightforward decision problem. Okay, we know what's going to happen next. So, question. Is the post-correspondence problem in P? Is there a polynomial time algorithm that can solve this problem, that can compute an answer to this decision problem? All right, I guess the last lecture was sufficient to immunize us against the case where maybe the answer is no, or maybe the answer is we don't know. It turns out the answer is a straight-up no. Now, we actually didn't see this very often in the previous lecture. So in the previous lecture, we talked about a lot of problems where we don't have polynomial time algorithms. But it wouldn't be correct to say something like, for example, we know that the partition problem cannot seem to be solved in polynomial time as far as we know. We have no polynomial time algorithm for it. But it would be incorrect to write that the partition problem is not in P. We don't actually know that. We have no way of knowing that at the moment. Maybe one day somebody will prove that, but currently we can't say that. Just because we have no polynomial time algorithm doesn't mean that the partition problem is not in P. And yet, you know, the slide sounds pretty definitive here. It turns out that the post-correspondence problem is in fact not in P. There is no polynomial time algorithm. Okay, well, fair enough, that happens sometimes. I guess what's the next one up? Is the post-correspondence problem in NP? And actually, even without knowing very much about the problem, we already know the answer to this question. Because if the answer to this question were yes, then a whole bunch of the previous lecture would need to be redacted. I mean, you'd have to retcon a whole bunch of that stuff. So if the post-correspondence problem is in NP, what does that tell us? Well, we already know that it's not in P. If we found out that it was in NP, that would actually be a proof that P is not equal to NP. And as I said, as of the recording of the last lecture, which I will admit was this morning, that was not the case. We do not have a proof that P is not equal to NP. It is unlikely that somebody proved that over lunch. Maybe they did. That would be profoundly strange if that were to have happened. So actually, we already know that the answer to this pretty much has to be no. It would be very strange if the answer turned out to be yes, especially given what I'm about to say in the rest of this lecture. A whole bunch of stuff would need to be changed if that were the case. Okay, wait a minute. So what have we shown? We've shown that this problem is not in P, and it's not in NP. And so far as decision problems go, problems with a true or false answer, I'm only aware of one problem that we've covered that we know certifiably is not in P and not in NP. And that is the problem of solving a game of checkers. We saw that in the previous lecture. We saw that if I give you a checkerboard of an arbitrary size and I ask you, can red force a win, even though that's a decision problem with a yes or no answer, it requires exponential time to solve. Okay, whatever. That means this is a sort of exotic problem, but I guess then the natural question is it exponential time? So before we go forward, though, I want to observe something, which is that I mentioned earlier that there is a sort of obvious notion of a certificate here. So if I were to give you a qualifying sequence, so in the case where the answer is yes, that there is a way to make the string on the top match the string on the bottom, if I were to hand that to you, wouldn't that be a certificate? It's pretty easy to iterate over these indices and construct the top string and construct the bottom string and verify that they're equal. And it's true, that actually would be a viable certificate. But there's a nuance, which is that we have no guarantee that the size of this sequence is polynomial in the input size. Remember that important point that I'm allowed to use every block as many times as I want. So maybe it is the case that the answer is true, but the only sequence sequence I can show you that will demonstrate the answer is true is a sequence of size, I don't know, 2 to the n, or even larger than that. And so that means, although I can indeed verify a certificate in a relatively straightforward way, I can't guarantee that the certificate will have a polynomial size. And as a result, I can't verify it in polynomial time with respect to the size of the input. Actually, one other minor note here. The size of the input for this problem isn't just n. It's actually going to be the size, it's going to be the number of blocks, and also factor in some information about the size of the strings inside of each block. Because, I mean, a block could contain a really massive string for all we know. In any event, there is no way to guarantee that the certificate, the sequence of indices, will be polynomial size with respect to the original input size. That's why the post-correspondence, well, that's one of the many reasons, it turns out, that the post-correspondence problem cannot be an NP. There are other reasons that we're going to see pretty quick. Okay, fair enough. So we know that the post-correspondence problem is not in P. We know that it's not in NP. Well, this is actually sort of exotic and exciting. This means we get to explore computational complexity beyond our usual comfortable realm of polynomial time and our sort of a little bit less comfortable but still tolerable realm of the class NP, which may or may not be polynomial. Maybe that means it's in the class exp. So recall from the last lecture, we did this very briefly, but we talked about the idea that there is this class exp, which is also sometimes called exp time, depending on your source, because there actually are other types of exponential functions we could use, like exponential space complexity or something. There is this class exp that contains problems that can be solved in exponential time. And it's sort of natural that it does turn out that P is a subset of NP, maybe or maybe not a proper subset, which itself is maybe or maybe not a proper subset of exp, because any problem I can solve in polynomial time, certainly I can solve that problem in exponential time. I do that by first solving it in polynomial time, and then just wasting time running out the clock until I've used up exponential time. Okay, fair enough. So is the post-correspondence problem in the class exp? Nope. Okay, this is getting a little bit strange. Fair enough. Well, fair enough, I guess, because there ought to be some complexity classes bigger than that. I mean, I can imagine running times that are more than exponential. I could try to put something together that seems like a greater than exponential running time, but that might be difficult because it's surprising what things turn out to be exponential functions. But I can certainly imagine that there are functions out there that are provably larger than exponential functions. There's no reason why the growth hierarchy has to end at exponential functions. Okay, fair enough. There are, in fact, plenty of complexity classes beyond exp, and there's actually also tons of other complexity classes contained in and intersecting with the ones we've already seen. So, for example, certain types of space complexity interact with the time complexity hierarchy in certain ways, in some ways that are unproven as well. There are conjectures about that. There are also various complexity classes that have to do with the use of random information or probabilistic computation. All sorts of fun stuff. I hope you have lots of fun in your future computational complexity course where those get covered. And it turns out that there are, in fact, computational problems that can be proven to require more than exponential time. So if we think of our post-correspondence problem, I guess that means it's somewhere out here, in the strange, spooky wilderness outside of the exponential hierarchy. Okay, what does that mean? I mean, I want to put this, I want there to be some sort of circle around it. I want it to be contained in some actual complexity class. Now, as far as trying to conceptualize algorithms that require longer than exponential time, we can actually revisit an old friend from back in lecture 30. And this was the first example of us scratching the surface of some pretty creepy things, some pretty weird properties lurking just underneath the friendly algorithms that we've come to know and love in this course. And it's the Ackermann function. So consider the Ackermann function. And if you go back to lecture 30, you can hear me talk all about how there really isn't just one Ackermann function. There are a whole ton of different ways of defining it that are slightly different, but all pretty much have the same effect. I chose this representation because it looks sort of familiar to us. So consider the Ackermann function, and we use this special spooky looking A to denote the Ackermann function. We first saw this back when we were talking about the union find structure. Now, we didn't really care so much about the actual Ackermann function. We mostly cared about its inverse, which we denoted by alpha. The idea behind the inverse Ackermann function is that it grows incredibly slowly, so slowly that for our purposes, we could sort of treat any algorithm with running time alpha as basically being constant time. And the reason why the inverse course Ackermann function grows so incredibly slowly is that the actual Ackermann function grows ridiculously quickly. So if you go back to lecture 30, again, you can hear me talk all about the weird way that that warps our sense of scale as far as how big numbers actually are. So the Ackermann function grows astronomically fast. And in fact, astronomically was the exact analogy I used back in lecture 30. And so, if there were a problem out there, and it turns out that there is, if there are problems out there where the only algorithms for the problem have running time Ackermann of nn, so for example, a problem with input of size n requires this amount of time, the Ackermann function has a growth rate that is greater than exponential. So that means that a problem that can only be solved by algorithms with that running time would definitely be outside of the exponential hierarchy, and it would be out here in the wilderness. Okay, that's a weird roundabout way of saying this, but I suppose what that means is that PCP, the post-correspondence problem, is one of those, maybe? Okay, so actually we could go further. Let's extrapolate all the way out. There is this class called R. R in this case actually stands for the word recursive, which is a sort of interesting tie-in. There's a reason for this, but it is something you'll have to learn about in a computational complexity course. The class R contains all decision problems that can be solved in any finite amount of time. In other words, any problem where there exists an algorithm that if you give it any input, any valid input to the problem, that algorithm will eventually give you an answer in a finite amount of time. It doesn't make any difference how long that amount of time is, as long as it's finite. So the set R is, of course, massive. It contains all problems that are, by our definition in this course, solvable problems. Even a problem for which the best algorithm required amount of time proportional to the Ackermann function, even that problem would be in the class R. It contains every solvable problem. And it's sort of good to know that. It's good to know that we've given a name to the set of all solvable problems. Okay, well, I guess mystery solved. Course over. There are actually also lots of other classes between exp and R, and as I say, there's lots of classes sort of in the middle. Have lots of fun learning about those in your future course. Okay, great. So we've got that figured out. The post-correspondence problem might take a ridiculous amount of time to solve, but we have this collection R consisting of all problems that are solvable. So that means that I guess all we can say about the post-correspondence problem is that it's in R, right? Right? Oh, this is looking weird. Okay. The answer is actually no. The post-correspondence problem is not in R. But I said earlier that the set R contains all problems that are solvable. And this is a pretty well-defined problem. I've given you a set of blocks of size n, and I'm just asking you whether there exists a set of blocks with this condition. All I want is a yes or no answer. That's the only problem I'm trying to solve, and we're saying here that it's not solvable. And that turns out to be the case. It is impossible for any algorithm to solve the post-correspondence problem in general. You might be able to write an algorithm that solves it in some cases, but you can't write an algorithm that solves it in general. No matter how much time you want to spend on it, if you want an algorithm that finishes in a finite amount of time, you cannot solve the post-correspondence problem. You can't do it in any amount of time. You can't do it even on the most powerful computer in the universe. Okay, oh, it's getting cold in here. This is a little bit weird. This is a little bit unsettling, a little bit disquieting. Actually, though, on the other hand, hey, wait a minute. This idea of the most powerful computer in the universe, that sounds pretty cool. Okay, so before we try and puzzle our way through why it is that the post-correspondence problem isn't solvable at all, I want to hear more about this most powerful computer in the universe. That sounds like lots of fun. Okay, well, behold, this thing is the most powerful computer in the universe. There it is. This is actually a sort of exhibit. It turns out that the computer that this thing is implementing is actually more of a theoretical construct, although we can actually create them. They can physically exist. And so when I say the most powerful computer, I should be careful about the use of that term. Power can mean a lot of things. I don't mean how fast it is. I don't mean how convenient it is. You will find that this does not offer much in the way of speed or convenience or usability. It provides a very minimal user interface. Instead, when I talk about the most powerful computer in the universe, I'm talking about its computational capabilities, the types of things it can compute. And so I'm saying saying that the most powerful computational device in the universe, the most powerful computational system, is this thing. Anything that you can compute, anything that you can ever imagine computing, anything that it's possible to compute can be computed by this. This is something called a Turing machine. A Turing machine is actually a type of theoretical computer. So Turing machines were invented as a sort of mathematical abstraction, as a construct to allow us to write proofs about the capabilities of a computer, in a sense, or at least that's how we're going to use them in this lecture. On the other hand, a Turing machine isn't a completely abstract notion. So a Turing machine is a description of a very simple computational machine, and you can actually build them. And here's an example of somebody actually having built one. There's a citation to where I got this image in the references with the video. And so physical Turing machines have in fact been built. You can think of that more as a hobby project because most of the time when we're using Turing machines, we're defining them in an abstract sense. So it's sort of theoretical computer. One other thing that's really interesting, that's especially profound after you've seen the rest of this lecture, is that the idea of a Turing machine was invented before any computers existed. So earlier in the course, when we were talking about dynamic programming, I mentioned that the first programmable computers, as we now know them, came into being around the mid-1940s, with a couple of asterisks, because it did turn out that an earlier computer from, I think, the late 30s, in hindsight, we were able to prove that it was programmable. And actually, we did that via something involving Turing machines, but I'll come to that later. It turns out that the Turing machine was defined by, unsurprisingly, by Alan Turing in the 1930s. Before any computers even existed, Turing had been able to specify what it meant for something to be the most powerful computer in the universe. Okay, so what is a Turing machine? This image doesn't give us really that much context. A Turing machine is a very simple device. So it consists of, and so the main operation is happening sort of around here, and you can see these two spools of what looks like sort of film or tape or something. So a Turing machine is a tape, and the tape consists of a bunch of cells, and into each cell you can write a symbol. And when we design Turing machines, at least by the basic definition, each Turing machine is hard-coded to do one particular task. Although we're going to come back to that restriction later. And so when you design a particular Turing machine, you can specify the types of data that can be written to each cell on the tape. It has to be some finite set of things. We'll call them symbols. So for example, I could define a Turing machine that's allowed to have these three symbols on the tape. And so each element of the tape is like the letter A, or the letter B, or the letter C. For our purposes, let's assume that when you define a Turing machine, you describe what it means for the tape to be blank. We don't want the tape to be formally blank because that's sort of implying there's a special symbol that corresponds to a blank space. You could do that. Plenty of sources do that. I think for simplicity, we'll do this. We'll assume that when the machine is created, the tape is pre-initialized with, let's say, the letter A, with one of the symbols that we define to be the default symbol. Okay, so the tape is a way of storing individual symbols in the cells of the tape, and the symbols are taken from a pre-selected fixed alphabet. Now, the Turing machine itself consists of this read-write head, and you can see the tape is threaded through the read-write head. And basically what happens is the Turing machine, at each step, will look at the cell of the tape right underneath the read-write head, and then perform some action. And the actions that are available are that it can modify the contents of that cell of the tape, and it can move the tape left or right. So it can sort of scroll along through the tape. That's all it can do. And the behavior, exactly what it does at each step, is specified in advance. We hard code that behavior into the Turing machine. So in general, we can specify a Turing machine over any alphabet of possible symbols. So for example, as I said a minute ago, we could use the set A, B, C. Or we could use the set A, B, C, D up to, I don't know, the letter Z. We can use any pre-selected fixed alphabet of symbols. We could, of course, also use, I guess because we're more comfortable with the idea of this being what's in a computer's memory, we could also use digits corresponding to the digits of some base. But it is actually sufficient to define all of our Turing machines to use binary. So any Turing machine, as it turns out, can be adapted to use binary as its alphabet, which means every cell of the tape contains either a 0 or a 1. Now, not every source prefers this definition. It turns out definitions are interchangeable. Any Turing machine that uses only 0 and 1 can also be adapted to use 0, 1, and 2. It's not really that big of a deal. I really like this because it feels very elegant to be working with the minimum possible number of symbols, and that's going to be 2 of them. Okay, so in this context, we're going to assume for our discussion in this lecture that a Turing machine works on a tape that contains only zeros or ones. And furthermore, we're going to assume that when the machine starts, at its very first step, the tape has been pre-initialized to contain only zeros. In other words, a blank tape is considered to be a tape containing only zeros. So at each step of execution, the Turing machine reads the cell of the tape right underneath the read-write head, and then it follows a very simple state-based transition to determine what to do next. And I'll explain what that means in a couple of minutes. There's a diagram that sort of helps us with that. Now, the tape functions as a memory, and theoretically at least, the tape has infinite length. Now, certainly, the requirement for an infinite memory does sort of get in the way of being able to physically realize a Turing machine. So how could we build a real Turing machine if the tape has to be infinite? Okay, well, don't worry about that, because it actually turns out that although the tape is infinite in theory, any computation that you perform will have to eventually finish if it's going to be useful. And in fact, I'll come back to this later in this lecture, but remember, all along when we talk about algorithms, we've assumed that algorithms are processes that are finite. They finish in a finite number of steps or a finite amount of time. And so if we're thinking about implementing an algorithm using a Turing machine, well, obviously, the algorithm will finish eventually. It has a finite number of steps. So any finite computation naturally cannot use an infinite amount of space. So although the tape is infinite in theory, any finite computation will only ever use a finite number of cells, which means if you implement a Turing machine, you could actually physically realize it using a tape of some particular size. We don't know in advance. That's something that's up to the individual implementation. So I might have some computations that could do everything on a tape of length 5, and some things that might need 10 billion elements on their tape. So although theoretically the tape is infinite, in practice, we have plenty of ways of implementing computations as long as we know in advance that they are finite, such that they only use a finite amount of tape. Now, the actual nuances behind that statement are a little bit complicated, because we'll see later in this lecture that deciding whether a computation is finite is not actually that easy, to say the least. However, if we know the computation is finite and can draw some reasonable bounds on how much memory it requires, which is clearly something we can do in practice because we do know how to write programs that run on our computers that have finite memory, then we can in fact implement them on a Turing machine where only a finite amount of tape is available. Okay, so the Turing machine itself, when we build the Turing machine, we hard code it with a program. And the program consists of a set of states. I'm going to number them starting at 0, along with one other special state that I'm going to call halt. And I'll explain what that means in a minute. And the idea is, at each step of execution, we're going to consider what state we're currently in. We're going to consider the contents of the tape cell underneath the read-write head. And that's going to be all of the information that we use to decide what to do next. So based on the current state and the symbol on the tape underneath the read-write head, we're going to write a symbol to the tape. We are then going to move the read-write head either left or right. I'm going to denote that by L or R. And then we're going to move into some other state. And we're allowed to go from one state back to itself. So the next state, if I wanted to, I could have S0 go directly back into S0. Now that might be a problem in some cases, but I'm allowed to do that. So the program for the Turing machine can be specified in a table that looks like this. The number of states in general can be any number, but it's hard-coded. So you could make a program with 1 billion states, you could make a program with 20 billion states, or you could make a program that only needs 5 states, like this one here. Now, the halt state, for my definition of Turing machines, I'm going to assume the halt state is a special one. There are plenty of other definitions that are equivalent where the halt state is one that you have to add yourself. That's no big deal. It turns out that there's plenty of flexibility in the definition. The one I'm using is mostly in the service of our discussion in the context of, the last lecture of an algorithms course. When you see Turing machines again in your future theory of computing course, you'll see that there are tons of equivalent definitions of Turing machines that that actually all have the same computational power. They are all the most powerful computer in the universe. The very simple one I've come up with here, where we are using binary on the tape, and there's a special halt state, and we hard code the state table, that actually is equivalent to a different kind of Turing machine where I'm allowed to use, let's say, 2 different tapes at once, or 3 different tapes at once, or a Turing machine where I can write 0, 1, 2, or, triangle, or whatever to the tape. It turns out that they're actually all equivalent to each other. Okay, so at each step of execution, the current state and the symbol that's on the tape under the read-write head are used to determine what to do next. And what to do next consists of write a symbol to the tape, and if I want to, I can actually write the same symbol back. So I could read a symbol from the tape and then write the same symbol back to the tape afterwards if I don't want the tape to change. Which means, even though I am theoretically writing a symbol at each step, there is still functionality to allow me to just keep the symbol the same. I just read a symbol and then write it back again. And then I move the read-write head either left or right. Now the definition for this that I'm going to use will allow us to have the read-write head stay still. That's fine. Although actually it turns out that even if I require it always to move left or right, the computational power is equivalent. I can achieve the same effect of standing still by just moving right and then moving back left again at the end of the next step. And then I choose a state to go into next, so that at the beginning of the next step, I will be in some other state, or in some cases, maybe I'll be back in the same state. Now, the action consists of writing a symbol, moving the read-write head, and then transitioning to a new state. I think the best way to justify this or to explain it further is to give an example. There is this special state called halt. Now, we're going to assume that the special state called halt is basically telling the Turing machine to shut down. So when the halt state is reached, execution stops immediately. The machine just turns off. It halts. And we would use, therefore, the state halt as a way of indicating the end of the computation. In general, we could write a Turing machine program that does some work, and when it's finished, whatever it was supposed to be doing, it moves into the halt state. And then we're standing by and watching it. As soon as we detect that it powers down, it enters the halt state, we can go and inspect what it left on the tape, and that could be its output. Okay, so what about this program here? I have this table that specifies a Turing machine. This is a very simple Turing machine program. If I start this Turing machine at state S0, I think that's a reasonable starting state, and the tape when I start the machine contains all zeros, so it's the analog of a blank tape, then the program will write the binary value 10001, which happens to be the binary representation of the number 17. It will then move the read-write head back to where it started, and then it will go to the halt state. I'll just demonstrate that. Okay, so here we go. So we start on a tape of all zeros. I will use this indicator to show where the read-write head is at each step. So we start on a tape of all zeros. We are in state S0, and the symbol we're looking at is symbol 0. Maybe it's been clarified by now, but if not, notice that the read-write head is only able to read the value right in front of it. It doesn't know anything about the rest of the tape. If it wants to learn about the rest of the tape, it has to move over and look at it there. Okay, so currently we're in state S0 at symbol 0. Okay, so we write the symbol 1, we move over to the right, and then we move into state S1. So here we are in the next state. We're in state S1. We are looking at a 0 now. Notice that the read-write head moved over slightly, and so I write a 1, move right, and go to state S2. And we keep doing this for a while. Eventually I hit state S4. And again, I'm sitting at a 0. You'll notice that in the meantime, I've written a bunch of 1s to the tape. Okay, so in state S4, if I'm looking at a 0, I write a 1, and then I start moving left. And notice that when I move left, I actually go back into state S3. Okay, so I write a 1, there I am, I've moved left. I'm now in S3, and I'm looking at this 1 on the tape. This is the 1 that I left behind earlier. The reason I did this is basically to leave a marker for myself, to remind myself I have to keep going back over to the left. I actually would like to spend another 20 minutes explaining how I wrote this Turing machine program, because it's sort of edifying, because it took a while, but I won't do that. You'll learn about that in a future course. Okay, so then I keep going through the state table, and eventually I actually work my way all the way back to my starting point here, and notice that here I'm in state S0 again, so I've actually managed to go back up through the state table and reached state S0, but now I'm looking at a 1. And so I write the 1 back, so I just leave it the way it is. I don't move the head of the read-write head, but I enter state halt. And so when the halt state is reached, notice that the value I've written to the tape is the value 10001, and that the read-write head was positioned back over where I started. Now I could modify the program so that it then scrolls back over and the read-write head finishes there if I wanted to. I could make the program, and we'll see in a minute, in fact, that's actually sort of an obvious statement given the result we're about to come up with. Okay, but first, one more example. Here's another very simple Turing machine program. Suppose that we start this Turing machine on a tape that already has some data written to it. So if I start this Turing machine, specified by this table, on a tape that contains a particular binary value, and I start the read-write head at the least significant digit, the rightmost bit of that value, this is a Turing machine that will add 1. So let's try that out. Here I'm going to start the Turing machine at this position on the tape. And you'll notice that I've already written to the tape the value, this is the binary representation of the value 187. What I want to do is demonstrate that when this machine finishes, it will have moved the read-write head back to the starting point, and the number written to the tape with the least significant bit here will be 1 greater. So this program has the effect of adding 1 to a binary value. And basically what it's going to do is, if I want to add 1, let's just try doing the binary addition here. So 10111 plus 1. How do I do this? Okay, well, 1 plus 1 is 0, carry the 1 in binary. 1 plus 1 is 0, carry the 1 in binary. So this is a 1, and then all the other bits get copied. So notice that really to add 1, all I have to do is to go and find the first 0 to my left, set that to be a 1, and then set everything to the right of that to be a 0. So I should expect that when I'm done, I have this value written to the tape. So 2 zeros, 4 ones, and then 0, 1, if I go from right to left. Okay, so let's start the machine. Okay, there we go. We're in state S0. We walk over to the left and we clear out the values of each thing until they're zeros, or actually we don't clear every 0. I'm getting ahead of myself. We get all the way to the first 0 that we find to the left. We set that to 1 and we crawl back. And when we finally hit the halt state, we end up with this. And this turns out to be the binary representation of the value 188. It is, in fact, the result of adding 1 to our starting value. And so we have now written a Turing machine that not only can actually place data on the tape, create an output on the tape, we've also seen a Turing machine that takes input and performs a modification. Now, it was a little bit complicated to add 1, but I hope that's enough to show you that if I wanted to add together 2 arbitrary binary numbers that, let's say, were placed right next to each other on the tape, I would be able to do that too. If I wanted to make a program that started with no input, wrote its own input value to the tape, and then added 1 to it, I could also do that because I have 2 programs already, one program to write a number, one program to add 1. And of course, a Turing machine is very clearly a pretty primitive computation device in terms of the operations it actually performs. It moves the read-write head either left or right, it modifies the symbol written to the tape underneath the read-write head, and it goes through a transition table that's provided and hard-coded in advance. We could obviously make very complicated programs for a Turing machine by making very large, complicated, cumbersome transition tables. But that's all it can do. And yet, although these operations are relatively primitive, they are sufficient to implement any algorithm. If you can describe a process as an algorithm, you can implement it on a Turing machine. This is a really big deal. But actually, before we unpack that further, I suppose it's a good time to remind ourselves about what an algorithm is. So wait a minute, what is an algorithm? Okay, well, I mean, any concept, like the concept of an algorithm, has some crunchy mathematical definition that you can memorize and recite to your friends so they can say, wow, you're pretty smart. You are studying something that's pretty complicated. And for the word algorithm, we've got one of those. Here it is. An algorithm is a precise and unambiguous sequence of instructions to perform a clearly defined task with finite resources. And of course, also, and critically for this particular aspect, the instructions have to be specified so that no creativity or cleverness is required to understand them or carry them out. Now, this is our definition of an algorithm from way back in Lecture 1. So it's about time we came back around to it. And it turns out that any algorithm that meets this definition of an algorithm can be implemented as a Turing machine. Any algorithm A can be implemented as a Turing machine. Now, this theorem is one of many facets of something called the Church-Turing thesis. And so it turns out that this has been proven in multiple ways. The one that's relevant to Turing machines, of course, is primarily the contribution of Turing, but equivalent results on similar computational systems, because it turns out there are computational systems that look nothing like a Turing machine, but have the same computational power. Similar results were proven by Church, as well as by other people. So actually it turns out that a lot of other famous people people, here's one of them, actually also contributed in some ways to the knowledge that led to what's called the Church-Turing thesis. And you'll see that actually the Church-Turing thesis is apparently so important and so all-encompassing that it gets the rare honor of being a thesis rather than just a theorem. So it got promoted a couple of levels above theorem. So we can use the Church-Turing thesis to reason about what problems can be solved using computation. Because if it's the case that any algorithm can be implemented on a Turing machine, if I am able to find a task that is impossible to compute with a Turing machine, well then that means that there can't be an algorithm for it. And that's a pretty big deal. This opens the door for us to be able to understand the limits of computation, what can be computed and what can't. And think about that for a minute. I don't know if we've thought about that before. There are some things that can't be computed. Now, of course, there are plenty of things I can imagine that we already knew can't be computed. I don't know how we compute love, for example. Okay, well, we knew about that. There are some things we can describe mathematically, so clear decision problems that we can describe formally in a mathematical way that cannot be computed. And that's a huge deal. So, for example, think of this corollary. This is based on what I just said. If a particular problem P cannot be solved by any Turing machine, well, then no algorithm exists to solve it. Because if an algorithm existed to solve it, by the Church-Turing thesis, I should be able to implement that algorithm on a Turing machine. So this allows us, finally, some way of assessing the limitations of computation. So the Church-Turing thesis states that any computation, so any algorithm that exists, can be implemented on a Turing machine, which means in turn that, we've specified lots of algorithms in this course, so clearly those can be implemented on Turing machines. It shouldn't surprise us based on seeing this theorem that if I wanted to implement Jarnik's algorithm or the Ford-Fulkerson algorithm on a Turing machine, I would be able to do so. But more broadly, literally anything you can represent as a computational process can be implemented on a Turing machine. So any valid computer program written in any language can be translated into a Turing machine. This is a really big deal because we've been studying algorithms through a certain lens, but what we're talking about now is the capabilities of any computer, whether or not we're thinking about it from the point of view of an algorithms person, whether or not it's a program where you would do big O or asymptotic analysis of the running time. Any computer program in any language can be translated into a Turing machine. In fact, there exist novelty compilers out there that will take a C program and compile it into the specification of a Turing machine, just to demonstrate this point. Not that we need such a thing to demonstrate this point. I can think of one program that would be very interesting to translate into a Turing machine. So one of the limitations I've already picked up on for Turing machines is that it's a bit weird that a Turing machine appears to be the most powerful computer in the universe, and yet, if I go think about a program for a Turing machine, it has to be hard-coded. The programs I'm used to, like on the computer I'm using right now, I can start and end at will. The computer that I'm working with right now can change whatever program it's running whenever I want to. I can turn the machine on, write a new program that didn't exist before the machine started, and then compile and run that program, but without shutting the machine off in the meantime. It does feel like if I have to hard code a Turing machine with a program, that does seem to limit its functionality a bit. Now, of course, it's a theoretical device, so the word functionality doesn't really have the same meaning we'd expect it to have, but there's one computer program that if I could implement it on a Turing machine would get around that restriction. So I think about valid computer programs. I can think of a program that actually any of us could write, a program that wouldn't really require much more knowledge about programming than you'd get from a first-year programming course. One program I'm thinking of is a Turing machine simulator. Now think about this. In the language of your choice, so C, Python, Java, C++, whatever, write a program that takes a transition table, like this transition table here, and simulates a Turing machine. So maybe you could use an array to represent the state of the tape. You'd end up with an internal state very similar to the examples I gave earlier of how the Turing machine ran. I think you will agree that it's not difficult to write such a thing. You're just writing a loop that takes a look at the current state, takes a look at the symbol at the current index on the tape, and then performs an action. It's pretty straightforward to write a Turing machine simulator. And if I can write anything as a computer program, then I can implement it as a Turing machine, which means a Turing machine is powerful enough that it can run a simulation of itself. We can actually design a Turing machine that simulates other Turing machines. And that's a big deal. In a theory of computation course, that's one piece of evidence that a Turing machine must be really powerful. Other models of computation, simpler computational devices, aren't able to simulate themselves or arbitrary instances of the same kind of device. If I write a Turing machine simulator and then I turn that into a Turing machine, we'll call that a universal Turing machine. A universal Turing machine is a special Turing machine whose program is reading a binary encoding of a Turing machine and then simulating it. So of course the input to a Turing machine, we can think about that as being whatever's written to the tape when the Turing machine turns on. What I could do is I could write a Turing machine simulator that parses a binary representation of a Turing machine. So basically I take a table like this and I represent it as a binary sequence of some kind. I could then write a Turing machine simulator that reads that binary sequence and runs the corresponding Turing machine. It just simulates that Turing machine. So I could write that simulator and then turn the simulator into a Turing machine. And before I know it, I have a single Turing machine that's capable of simulating any other Turing machine. I have one device hard-coded with a simulator that can run the specification to an arbitrary Turing machine. And we'll call that a universal Turing machine. And a key result that we're just going to rely on for this lecture is that such a thing does exist. I could write a Turing machine simulator, and if I can write a computer program for something, I can implement that thing on a Turing machine. So for example, I could take this program from earlier. I could encode this transition table as a binary string. There might be some other details in there besides the actual table. So I might have to include information on how many rows the table has and stuff like that. The number of total states. I might also want to include information about the initial state of the tape, but I could do that. I could encode all of that into one binary package, and then I could write a program that reads that binary package and runs the corresponding Turing machine and simulates it. So the universal Turing machine then parses that binary encoding and simulates the execution of the machine that I've encoded. So since any program can be implemented as a Turing machine, and since a universal Turing machine can simulate the execution of any other Turing machine, if I create a single universal Turing machine, that device is capable of executing any program that could ever exist. And that means that a Turing machine is the most powerful computer in the universe. We're not done just yet. We don't quite know why post-correspondence problem, which doesn't seem like it's really that difficult, why that for some reason can't be solved, even by a Turing machine, which we've now been told is the most powerful computer in the universe. And actually also there's another lurking question, which is, hey, wait a minute, my laptop does seem to be a lot more powerful than a Turing machine. I mean, that is, in the time that I've spent giving this lecture, recording this video, the calculations done by my laptop have certainly been, a lot more numerous, not to brag, but a lot more numerous than what a Turing machine with a piece of tape could have done in the same amount of time. So one thing to observe is, and this goes back to our idea of reductions from the last lecture, I can write a computer program that simulates a Turing machine. I could run that simulator on my laptop. And in fact, earlier in this lecture, I showed off a simulation of a Turing machine that was the result of me writing a Turing machine simulator. And I realized that if a Turing machine is a powerful computing device, if it's the most powerful computer in the universe, and I can simulate a Turing machine on my laptop, well, that means my laptop is capable of any computation the Turing machine could do. If a Turing machine can do some particular computation, I could have my laptop do that same computation by simulating a Turing machine on my laptop. What that's telling me is, in a sense, that's a form of reduction that shows me that any device that's capable of implementing a Turing machine simulator must be at least as powerful as a Turing machine. And so, of course, and this is a nice happy ending, it turns out that my laptop and your laptop, and probably the device that you're watching this video on if it isn't a laptop, is in fact also tied for being the most powerful computer in the universe. Any computing device sufficiently powerful to simulate a Turing machine is the most powerful computer in the universe. Now you can see how it says any computing device, but it also says programming language. That's weird. So a programming language can be said to have computational power as well. There are very simple languages that we've used. For example, if you think about typing an expression into your calculator, that is a form of language. I mean, if I type in an expression like 6 plus 10 plus 9 times 17 or something like that. Well, we could interpret the use of arithmetic as a sort of primitive form of programming language. Actually, if you want to know more about how we parse such a language, go on back to lecture, what was it, lecture 13 or 14 or something? We actually talked about expression trees, so we actually know about this already. So this is a form of programming language, but basic arithmetic, up to there's a couple of asterisks on this, but basic arithmetic is a fairly primitive language. It doesn't have the same computational power as, I don't know, Python or C or something. So programming languages do have a notion of computational power. If a programming language is powerful enough that I can implement a Turing machine simulator in that language, well, then that means I can perform any computation at all in that language. So the fact that I can write a Turing machine simulator in the C language or in the C++ language or in the Python language or even in the Java language means that all of those languages are as powerful as a Turing machine. And we have a word for this. We call it Turing-Complete. Anything, whether that be a device or a programming language, or sort of strangely a computational problem, remember that one for later, anything that is capable of simulating a Turing machine is at least as powerful as a Turing machine. And since Turing machines are the most powerful computational device, that means that they are tied with a Turing machine as the most powerful computer in the universe. We call such things Turing-Complete. So if a programming language is Turing-Complete, that means you can use it to implement any algorithm, any task. And of course, all of our favorite languages like Python and C and C++, uh-oh, I ran out of space. I guess my list has to end there. All of my favorite programming languages are Turing-Complete. And actually, if you look up the term Turing-Complete, you can find, I think Wikipedia has a great list of this, there are all sorts of other languages and things, devices and computational problems that turn out to be Turing-Complete, even though that's completely weird. Like there are devices that you never expected to need that amount of computational power that actually are Turing-Complete. You can use them to simulate a Turing machine. And of course, knowing about reductions from the last lecture sort of helps us get a handle on why this is. We've reduced the problem of computing anything to computing something on a Turing machine. Any computational problem can be reduced to Turing machine computation. If I can then reduce simulating a Turing machine to any other setting, like Python programs or my laptop, then I have shown that my laptop is capable of computing anything. And so, of course, since I can implement a Turing machine simulator in all of these languages and even this one, those languages must have the same computational capacity as a Turing machine, and so they are Turing-Complete. Now, actually, as I observed earlier, we can compile a C++ implementation of a Turing machine simulator, or whatever other language we choose, into machine code for our processors. Or moreover, whether we compile the code or not, we are capable of using the processors in our laptops and phones and whatever to run Turing machine simulators, which means that the processor in my laptop and in your laptop must be Turing-Complete as well. It's capable of performing any computation. Now, certainly it's a lot more convenient to use a laptop than an actual Turing machine. There are lots of other features that laptop processors or desktop processors or whatever have that go beyond computational capability, for example, speed, and for the most part, usability, that are also pretty important factors. And in general, it's true that any Turing-Complete system can simulate any computational system, whether that system is Turing-Complete or not. So even a more primitive system can certainly be simulated by a Turing-Complete system. In other words, any problem you can solve in C++, you can also solve in Python. It might be slower, it might be more tedious, or maybe it's faster, who knows, but you can do it. There is a way of performing that computation. Factors like running time are independent of this. So it's true that there are certain settings, like, in general, if you write a C program for something, it will be faster than a Python program, broadly speaking, if you are a competent C programmer. However, the computation is still possible in Python or in any other language that's Turing-Complete. Now, as I said a minute ago, a Turing machine is the most powerful computer in the universe. Every computation that can be performed on a Turing machine. No system can have greater computational power than that. All right, so I want to build up to this issue of the post-correspondence problem from earlier, but I want to sort of take a sidestep and talk instead about this other problem, which is also a very famous problem in the meantime. It's called, I'm going to call this decision problem, does it halt? And what's going to happen is I'm going to give you a Turing machine M encoded as a binary string. So we know already that you can take the transition table for a Turing machine and all other relevant information, and you can turn it into a binary representation. And we also know that I can certainly create Turing machine simulators in a lot of different settings, in a language or on another Turing machine, that read the representation of a Turing machine and simulate it. So I have this decision problem. I'm going to give you a Turing machine, and I want you to answer yes or no. If I run this Turing machine, starting on a tape containing only zeros, does it ever halt? So give me the answer true if it does. I don't know how long it takes, but if it ever halts, after any amount of time, if it ever reaches the halt state, return true. If not, return false. Now, one important note is that the only thing it can do besides halting is entering an infinite loop. I mean, either it eventually reaches the halt state or it goes around in circles forever. It goes through, it enters some kind of infinite loop that never ends. So either it finishes, it enters the halt state after a finite number of steps, or it continues running for infinity. So this problem, does it halt, evaluates to true if the Turing machine I provided ever halts after any amount of time, even an incredibly large amount of time, and if it doesn't halt, then it returns false. Here is my claim. There is no algorithm which can solve this problem. You cannot write an algorithm that will give you an answer for every Turing machine that I could provide. It is impossible. And so if we think about this in terms of the fact that it's a decision problem, we have a word for that. It is an undecidable problem. This is something that is beyond the capability of computation. No computer, not even the most powerful computer in the universe, could ever give a correct answer to this question in all cases. Now, sure, it's true that we could actually design programs pretty easily that are able to give a correct answer in some cases. So, for example, an easy one is you could write a Turing machine simulator that runs M for, I don't know, 100 seconds. And then if it finishes, you could return true. But how do you know if it's not finished after 100 seconds that it's never going to finish? So you see what I mean? So it's true that we could design algorithms that approximately answer this question. The statement being made by this claim is that there is no algorithm that can solve it in general for every possible input, which means this decision problem is beyond the reach of computation. It is undecidable. Now, I want to prove this. We could prove this directly in terms of Turing machines, but again, we have to save some fun for your next few courses. And actually, if we do that, if we want to prove it directly in terms of Turing machines, we need some, I don't know if the word background is right, we just need to spend a bit more time on definitions and talking about how to create Turing machines, and that isn't really relevant to our context. So what I'm going to do is, I'm going to rely on the fact that I stated earlier that a language like Python, because we can write a Turing machine simulator on Python, Python is Turing complete. So I'm going to take this classic representation of the problem and I'm going to move it over to a similar, it turns out equivalent problem, but stated not in terms of Turing machines, but in terms of Python programs. It actually turns out this is the same problem because any Turing machine can be converted to a Python program and any Python program can be converted to a Turing machine. Okay, what do I mean by that? Well, if you give me a Python program, because that's a program on a computer, there is some way of translating that to a Turing machine. Okay, that's one direction. If you give me a Turing machine, I can actually run that Turing machine using Python by just writing a Turing machine simulator in Python and running it there. So therefore, it is actually true that there is a correspondence between Python programs and Turing machines. Okay, so I've transposed the problem to the Python language. So here I'm going to give you as input a Python program P. And it's going to be represented as a string of Python code. So Python is a great language for this because we know already that Python has great introspection, reflection features, and whatever. It's very easy to understand that Python code can be represented as text. And at any moment during a Python program, you can run Python code written as a string. So I'm going to give you a Python program represented as a string of Python code. You can also think of this program as being represented by a file stored on disk, because ultimately a file stored on disk is just a string of Python code if it's a Python source file. And the decision problem is, I want you to give me the answer true if the program P ever terminates. So I'm going to run the program from the command line. So I type something like this on the command line, Python, my program .py. I'm going to sit there and do nothing. And if, as a result of running this program and doing nothing, the program would ever terminate, I want you to return true. Even if it takes a ridiculous amount of time to do that, I want you to return true. If instead the program would never terminate, I want you to return false. That's the decision problem. I'm going to call that problem, does it halt? Okay, so again, the same claim applies. There is no algorithm that can take the representation of a Python program as source code and answer this question. Certainly, if you want an answer, one way of trying to get an answer would be to run the program yourself. But remember, if you run the program yourself, when will the answer become false? Like, how long do you have to wait? That's a bit of a tough one. What I'm asking is there an algorithm that can read the source code, look at it, so just figure out what it does, and tell you, yes or no, does the program terminate? This algorithm that I'm talking about doesn't necessarily have to run the program at all. It could just inspect the code and give an answer. And actually, from your own programming experience, you know that there are pieces of code you could look at without ever running them and just decide based on inspection whether the code ever halts. So, I mean, I do this all the time when I mark first-year programming exams, right? So I can look at some code and say, well, that code clearly enters an infinite loop. Or I can look at some code and say, that code clearly doesn't enter an infinite loop. An obvious example is, if I give you a program that contains no loops, clearly it's not going to enter an infinite loop. And so it's obvious that there is some facility for people, and maybe to some extent computer programs, to look at code and draw some inferences. My claim is there is no algorithm that in general can take any Python program and tell you yes or no, does this program ever terminate? And I want to write a proof of that fact. The proof is by contradiction. Okay, so suppose that there does exist an algorithm to solve the does it halt problem. Now what this means, because we know that Python is Turing complete, that means that any algorithm that exists can be written in Python. Maybe it's cumbersome to do so, but it can be done. So if there exists an algorithm for the does it halt problem here, that means I could write that algorithm as a Python function, for example. So I'm going to do that. Consider this program that I've just invented. Let's suppose that I create a program, and it's actually significant to the proof that I say this, and I store the program in a file called haltingproof.py. So I make a source file called haltingproof.py. The contents of the file, of course, are a string of text. It's a string corresponding to this source code here. So I make this Python program. In the Python program, I'm going to have an implementation of the algorithm for the does it halt problem. So again, my proof by contradiction is, suppose there exists an algorithm for this. And if there exists an algorithm, I should be able to implement it. So I do. It's there. I haven't given the implementation for reasons that I think should be obvious by now, because there is actually no algorithm. But suppose I have the implementation sitting there. Okay, what else does this weird-looking program do? It's a very strange program. So I have this function that solves the does it halt problem. I give it a string of text containing some Python source code, and it answers yes or no. Does the program ever terminate? Okay, what do I do next? So I've defined the function, and in the main body of my program, the first thing I'm going to do is open up the source file for this program. So this whole thing is in a file called haltingproof.py. So the first thing the program does is it reads its own source code into a string, and we'll call that string S. Okay, and then it just does this very simple conditional statement. So it then calls the does it halt algorithm on its own source code. And you can see that this is getting a bit weird. It calls the does it halt algorithm on its own source code and then takes one of two paths. So if the answer comes back true, so that would be this block here, then the program enters an infinite loop. And you can see, so this is, if you're not a Python person, if I say while true and then the word pass just means do nothing. So this is an infinite loop. It just goes on forever and doesn't generate any output or do anything else. It just loops infinitely and the program will never terminate if I reach line 10. So if does it halt returns true, and remember that does it halt returns true if the source code I provided ever halts. Okay, so if that happens, then I enter an infinite loop. If does it halt returns false, then I immediately exit. Now remember that does it halt returns false if the code that I provided enters an infinite loop. So if that happens, I'm going to exit my program immediately. Now pause the video and think about this for a minute. So what does this program do? So just think about that. Like try and think about the cases for what happens when I run this program, assuming that I have a valid algorithm for does it halt before I get to the punchline. Okay, I'll assume you've done that. So does this program, we're talking about whether programs terminate or not. Here's a program. Does this program terminate or not? Does this program terminate or does it enter an infinite loop? So clearly, if I run the program, one of those two things is going to happen. So I run the program. What happens? Well, let's see. There's two cases. I mean, we can see in the source code there is an infinite loop and there is a call that exits the program. Which one of those things happens? Well, let's try and figure it out. I guess because there's an if and an else, there are going to be two cases. Case one, if haltingproof.py ever terminates, well, that means, because I've given the source code of haltingproof.py to does it halt, if haltingproof.py ever terminates, then this returns true. But if that happens, then I enter an infinite loop. And the program I'm in is haltingproof.py. So the effect of what I've just said is that if haltingproof.py ever terminates, then haltingproof.py enters an infinite loop. Well, that's obviously a contradiction. Okay, so case one gives us a contradiction. What's case two? Well, case two is the situation where does it halt returns false, which is going to correspond to the case where the source code that I provided enters an infinite loop. Okay, but the source code I provided was this code. So that means if haltingproof.py enters an infinite loop, then the call to does it halt returns false. But the very next thing I do is exit the program, which means the program terminates. So that means that if does it halt enters an infinite loop, then does it halt terminates. That's also a contradiction, obviously. Okay, so that gives us our proof by contradiction. And as has become tradition, let's scroll back and try and figure out which assumption resulted in this contradiction occurring. Where have I made an assumption? Oh yeah, it's here. The only assumption I made was, suppose there exists an algorithm to solve this problem. And if I make this assumption, I end up with a contradiction. And we know what that means. That means that no such algorithm can exist. The only assumption I made was that this algorithm existed, and clearly if it exists, a contradiction occurs. Therefore, no algorithm exists to solve this problem. That means that the does it halt decision problem that I've written down here for Python programs is undecidable. There is no way of ever implementing an algorithm that will answer this question correctly in all cases. That's not just true of Python programs. You could do the same thing in Java or C++ or Fortran or whatever. Those are all Turing-complete languages. Although I will add that I've gone through this proof over the years in many different languages, in different courses over time as language preferences have changed. And boy, is it nice to do it in Python. It is a very elegant looking proof if I use Python as my language. Python is great. So there is no way that I could ever solve this problem using any Python code or any C++ code, or as it turns out, using a Turing machine either. So if I go back to my original formulation of the problem for Turing machines, since Python is Turing complete, I can turn any Turing machine into a Python program by just basically representing the Turing machine state table and then writing a Turing machine simulator in Python. And so that means if I could solve the does it halt problem for Turing machines, I could solve the one for Python and vice versa. And so it actually turns out that that implies that the Turing machine version of does it halt is also undecidable. These are problems that cannot be solved by any computational system, even the most powerful computer in the universe. Now, I've called this does it halt for the sake of giving it a pithy, easy to recognize name. In general, this is called the halting problem. And if you look up the halting problem, and in fact, actually by now, if you're a computer science student, you've probably heard that term once or twice. That is, you've heard it slightly in your periphery while walking down the hallway. It's a pretty big deal. So the classic example of a problem that's incomputable, that is undecidable, that cannot be solved by any computer is this thing called the halting problem, deciding whether some arbitrary computer program or Turing machine ever terminates. Now, we saw last time that once we were able to show that there were certain problems, if we think about in the previous lecture when we were talking about NP completeness, we were able to show via the Cook-Levin theorem that there are certain problems that every problem in NP can be reduced to. Once we know of some problems with that property, we can then branch out and show that other problems have that property too. We have now shown in this lecture that the halting problem is undecidable. There is no way to solve it. I can use reductions to show that there are other problems where if they are solvable, then so is the halting problem, which in turn means that those other problems have to be undecidable as well. Now, a common question here, and one again that I had in my own theory of computing course when this was brought up is, hey, wait a minute. If I want to know whether a Turing machine halts, can't I just run it? I mean, obviously, if I run the machine M, either it will halt or it won't. So isn't that a solution to the halting problem? And the answer is no. And it's because our definition of an algorithm, so something that solves this problem, an algorithm to solve this problem, must finish in all cases. It's true that if I run a Turing machine and it does halt, I will eventually get the answer I'm looking for. So if I just wait long enough, any Turing machine that eventually halts will eventually halt. So I will eventually get back an answer if the answer is true. But what if the answer is false? When do I stop? How long do I run the Turing machine for before I can conclude that the answer is false? That's the issue. Running the Turing machine doesn't give me any exit point where I'm allowed to say that the answer is false. So it is possible, obviously, to evaluate the does it halt function in some cases. I could run a Turing machine, as I said earlier, for 100 seconds or 100 steps. And if it's halted within that amount of time, I have an answer. However, there is no algorithm that in a finite amount of time can give me an answer, whether it be true or false, for any program or any Turing machine. And so, actually, I should add that there actually are plenty of cases where it is possible to determine that the program has entered an infinite loop. Just like how, if I show you a Python program, so here is an example of a Python program, while x is greater than 0, x equals 1. Well, this is an infinite loop. Notice how, even though in theory solving the does it halt problem is impossible, I can solve it in specific cases, both when the answer is true and when the answer is false. And you could write analysis logic that could identify this as an infinite loop. There actually are compilers out there that look for things like that. But they can't be correct in all cases. That's the key point. There is no algorithm that solves this problem in general. There are algorithms that solve it in certain specific cases. I'll come back to that in a few slides. So it is not possible in general to evaluate this decision problem does it halt in a finite amount of time when the result is false, because the machine literally runs forever if it enters an infinite loop. And there's no way for you to conclude that that's happened in general. There are ways for you to conclude it's happened in some cases, but not in general. And we recall from our definition of an algorithm from like 5 slides into lecture 1 that any process that doesn't finish in a finite amount of time for every input is not an algorithm. And so if it's true that there is no way of evaluating this decision problem in a finite amount of time for every input, then there cannot be an algorithm to solve it. Okay, so where does that leave us? Well, I mentioned earlier that we have this special complexity class R, which consists of all problems that can be solved in a finite amount of time. We now have some context for what that actually means. So another way of phrasing the meaning of the class R is talking about something called Turing decidability. So a decision problem is considered to be Turing decidable if it can be solved by a Turing machine in a finite amount of time, regardless of whether the answer is true or false. It's true that the halting problem is solvable in finite time when the answer is true, because you could just run the machine until it halts. The problem is that the halting problem cannot be solved in a finite amount of time when the answer is false, in general. So the complexity class R contains all Turing decidable problems. And in fact, there are sources out there, there are books on complexity that don't even call this class R. They just call it the class of all Turing decidable things. So those definitions are interchangeable. I like the name R because there's something sort of angular about it, having a single character name. And also because, as I mentioned earlier, R actually stands for recursive. Because the formal definition of what a recursive function actually is, which turns out to be extremely complicated of a definition, like there's a lot to it, it turns out that the set of all things that can be computed actually is equivalent to the set of all recursive functions. And that is also equivalent to the set of all Turing machines. That is, anything you can compute on a Turing machine can be thought of as a certain form of recursive function and vice versa, which is really interesting. That's one of the reasons I like calling this class R. Okay, so since the halting problem is undecidable, we know that this does it halt decision problem is not in R. It is not a solvable problem. No computer that has ever existed or could ever exist could solve this problem in general. We could approximate a solution. We could try our luck with just waiting a long time, but in general, there is no algorithm that will solve this problem with 100% accuracy, with perfect accuracy, in a finite amount of time. Now, as I mentioned a minute ago, since the halting problem is undecidable, any other decision problem that would imply a solution to the halting problem has to be undecidable too. And this is where we can bring in the concept of a reduction. So here's an example of some sort of adjacent problem. It's called, does it generate output? I'm going to give you a Python program P. And the decision problem is, tell me true if the program ever generates literally any output of any kind. and tell me false if it doesn't. That's it. Just decide whether or not the program generates even one character of output. And it turns out, and I don't care whether the program terminates. So if the program generates some output and then enters an infinite loop, well, then the answer is true. If the program generates some output and then halts, well, the answer is still true. So regardless of whether the program terminates, I want to know whether it generates any output. So this is not directly solving the halting problem, but via a reduction, we can show that we can, in fact, use this to solve the halting problem. And one way of visualizing that or understanding it, and a way I like to use, is again to leverage the idea of simulation. So I can reduce the does it halt decision problem to does it generate output. In other words, now this reduction, by the way, is just a regular reduction, an arbitrary one, not a polynomial time reduction. We're no longer talking about polynomial time. We're talking about, in general, the idea of reducing one problem to another. So I have no requirement to show that this takes some specific amount of time, just that it takes a finite amount of time. So I can reduce the does it halt problem to does it generate output. So if you give me an algorithm to solve this, that would imply an algorithm to solve that. And in turn, because we know there is no algorithm to solve this, that means there can't be an algorithm to solve does it generate output either. Okay, here's a brief sketch of the proof. So for example, suppose I'm going to write this as pseudocode just because, well, you'll see. Suppose that I implement this as a Python program. And it takes the source code of a program P, which is the specification for my does it generate output program. It takes some source code P. And then what it does is it simulates program P using a Python simulator. However, when it's simulating that program, if program P generates any output inside the simulator, we just ignore it. We just discard any output produced. So this program, the outer program, the one implemented by this function here, does not produce any output under any circumstances during line 2. We just simulate the program silently in the background and ignore any output the program attempts to produce inside the simulator. And we know that we can do this. We know that if we write our own simulator, we can set all sorts of weird conditions for how it works. Okay, so on line 2, I simulate the program P. And I keep simulating it for as long as it takes, even forever. If the program never terminates, I'll just be stuck on line 2 forever, simulating the program for all eternity. If the program ever terminates, I print out the text program terminated. Okay, so I simulate the program. It's also worth observing that you might be thinking, wait, what's this Python simulator? So we know that Python is Turing complete, which means I can simulate a Turing machine in Python. I can also simulate Python inside of a Turing machine, and so clearly that by itself is enough for me to know that I can write a Python simulator inside of Python, either directly or indirectly. So I can do this. And in fact, if you want one, such things do exist. You can actually go use a Python simulator that you can run from inside of Python. Okay, so I do that. And any output produced inside of the simulation is just ignored. So this program never produces any output at line 2. If I ever get to line 3, I print out program terminated. And notice that this is the only output that will ever be produced by the program I've created here. This program only ever produces output at line 3. And maybe now you can see the problem. The only time that there's output produced by this program is if program P halts. Which means if I have a way of solving the does it generate output problem, I actually have a way of solving the halting problem. Because if this program generates output, then P halts. If this program does not generate output, then P does not halt. And so therefore, I have found a way of reducing the does it halt problem to does it generate output. And of course, that means that there cannot be an algorithm for this. So therefore, the does it generate output problem must be undecidable. Now that's, I mean, maybe you look at that and say, that's a fun toy example. Great. So we have this one sort of abstract problem that's undecidable, the halting problem. We have this other sort of weird toy problem that isn't too far removed from it that's also undecidable. How does this affect me? Now, you might especially be saying this if you don't consider yourself as much of an algorithm person as I do. I mean, I think this is fantastic and really fascinating. But you say to yourself, hey, I just learned about algorithms because I want to get out there and write some code. How does this affect me? Well, you'll find that it affects you in a lot of ways, and in a lot of very immediate ways, in fact, especially if you find yourself writing code in compiled languages, or moreover, if you like code that's fast. So let's consider code optimization. So the best way of talking about this is talking about a language like C or C++. So a C or C++ compiler will typically contain optimization logic to ensure that the machine code that they generate is as fast as possible, or maybe requires as few instructions as possible. So the idea is we want to optimize the code that you wrote in C into the most efficient or compact machine code representation. If you want to do this with a C compiler like GCC, you would use the flag -03. If you want to use a C++ compiler, you do the same thing with the C++ compiler. Or you could do I think O3 is optimizing for high speed, O2 is optimizing for compact code, O1 is optimizing a little bit, but not so much that the compiler becomes slow. So there are these built-in optimization procedures. And so I guess a natural question is, can I design a compiler optimizer that is guaranteed, if I give it some piece of C++ code, to produce the absolute most efficient machine code possible for some particular architecture, like the architecture for my laptop or my phone or whatever? Now, we know already that's obviously an optimization problem. I want to make a program that runs in the fewest instructions, or a program whose code consists of the fewest number of instructions. But we like talking about decision problems. So I could phrase that optimization problem as a decision problem using pretty much the same adaptation we saw in the previous lecture. So I'm going to do that here. This is a problem called code optimization. You give me a C++ program called P, and that's represented by some string of source code. You also give me an integer K, and the decision is true or false. True if there exists a program, I think they should say, maybe we'll say some program. If there exists some program, some machine language program, using at most K instructions on whatever architecture you care about, that produces identical output to P in all cases, or whatever other criteria you want to impose. Identical output is the easiest one for this example. If we generalize it to the criteria that's actually used by compilers, the same result holds, it turns out, but it's a bit more messy to establish it. So the idea is, of course, if I write a program in C++ and the compiler performs manipulations to make it faster, that does fundamentally change what the program's doing internally. But I don't care as the programmer as long as the outward behavior of the program is the same. One way of thinking of that behavior is it generates identical output in all cases, for example. And so, of course, we want to ask, can I write a compiler that generates a program with at most K machine code instructions? That's one way of sort of quantifying the optimization version of the problem as a decision problem. And so the question really is, this is a way of us getting at the question of, can the compiler generate perfectly optimized machine code, the guaranteed optimal machine code in all cases? But it turns out that it can't, because if it could, then the algorithm it was using, whatever algorithm did this perfect optimization, would also solve the halting problem. And we can't solve the halting problem. That's impossible. And that means if you want to write a compiler that optimizes, the best you can hope to do is a good job, not a perfect job. You can write a compiler that optimizes really well in most cases, but not in all cases. And here's one way of proving that. So here is a program, I'm going to call this optimization breaker. And it's going to work like this. So the idea is, suppose I had some C++ compiler that was capable of producing perfectly optimized machine code. And in our context, that means machine code using the minimum number of instructions that still produces the same output in all cases. Okay, so suppose we have a compiler that's able to do that. And then I'll take this pseudocode and write this as C++. Now, I should be careful again to observe that I can't just say that any piece of what I claim is pseudocode works as C++, but if you look at it, I hope you'll agree this is something we can do in C++. So I have M corresponds to a transition table that I hard code into my C++ code for some Turing machine. Whatever Turing machine you want, I will hard code it into my program. Then I write a Turing machine simulator in C++, which again isn't a very difficult task. You can go ahead and try doing it yourself if you're a C++ person. It'll only take you maybe an hour or so. And then after the simulation ends, if the simulation ends, I print out program terminated. So you'll see this is a very similar reduction to the does it generate output task from earlier. And so what I'm doing here is basically running some arbitrary Turing machine until it finishes, and maybe it never finishes, and in which case the simulation stalls on line 3. If it finishes, I print out program terminated. The program generates no other output at any point besides on line 4. And so we proceed basically as in the proof we did earlier. So if the Turing machine never halts, no output is ever generated. And if no output ever gets generated, then the perfectly optimized machine code representation would just consist of an infinite loop. It might not even be that, because you could argue that if no output is generated, the program could just end instantly with no output. But in any event, the shortest optimized machine code representation will be very easy to identify. It's a program that generates no output and then just gets stuck and runs forever. And so if I optimize that all the way down to its minimum representation, that would just be one empty infinite loop. And it would be easy to identify that I've produced that. That is, the minimum version of an infinite loop on most architectures is very easy to spot. If, on the other hand, the simulation ever does end, because the program does terminate, then the perfectly optimized machine code wouldn't even bother including any of this stuff, because none of this stuff generates output. All it would do was print out program terminated. And you can see the problem. If a compiler could perfectly optimize this program, that would mean I can solve the halting problem. It would be very easy to identify the case where the program M, the Turing machine at issue, halts, and the case where it doesn't. And we know that it is impossible for any algorithm to know whether a Turing machine halts. And so this means a compiler that could do perfect optimization would be solving the halting problem, but it can't. The halting problem cannot be solved. Okay, so as a result, we can conclude that the best we can do with compilers is do good optimization, to try and optimize as best we can and not assume that perfect optimization is possible. Which actually is sort of liberating if you think about it. If you know that the problem you're trying to solve is formally unsolvable or undecidable, then if you can make even any progress on it, you're doing a pretty good job. Okay, so let's go back to the beginning. What does that mean about the post-correspondence problem? Now, actually, it turns out that really the most satisfying resolution here is something I can't fully provide because it would involve a very long proof that I don't think any of us have any patience remaining for. And again, because it's a fun proof that you might, well, I don't know about fun. It's a proof that you might see in some future course. So basically, the issue with the post-correspondence problem is, although the post-correspondence problem looks rather straightforward, and in my mind, it has a lot in common with the partition problem in that sense. It just feels like a puzzle like this can't be that difficult to solve. It might take a long time, but it can't take that long. Just like the partition problem felt like it ought to be solvable in polynomial time, if things like minimum cost maximum flows can be computed in polynomial time. And yet it turns out that it is possible to reduce the halting problem to the post-correspondence problem. And that, of course, means that the post-correspondence problem is undecidable. It cannot be solved. No computer, no algorithm can ever exist that solves the post-correspondence problem in all cases. Now, I can summarize sort of how to do that. So basically what happens is you can take a Turing machine M, and in some finite amount of time, maybe a long time, you can actually convert it to a collection of blocks for the post-correspondence problem, such that the Turing machine M halts if and only if there is a solution to the post-correspondence problem over that collection of blocks. And of course, that means that if you could solve the post-correspondence problem at all, that you would be able to solve the halting problem. And that means that you can't solve the post-correspondence problem in general. As a result, the post-correspondence problem is undecidable. There is no algorithm to solve it. But that said, hey, can we solve it anyway? I mean, I've actually already mentioned this a little bit earlier in the lecture, but hey, wait a minute, this problem doesn't seem that difficult. Maybe I could try writing an algorithm that solves it in some cases. And of course I could. The result that it's undecidable is only this statement of the problem, this general statement. One thing you might have picked up on is the actual amplification of difficulty. The reason the problem is so difficult is because I'm allowed to use each block as many times as I want. And you can also think about using a particular block a huge number of times as sort of corresponding loosely to what might happen inside of a loop in a computer program. That is sort of how the reduction ends up working. I might see the same sequence of blocks in my reduction of a Turing machine to a bunch of blocks. I might see in a valid sequence the same sequence of blocks showing up over and over again corresponding to some loop happening inside the program. So what makes the post-correspondence problem so difficult actually is that feature where I can use each block as many times as I want. If I were to change the problem slightly to restrict it, I actually might be able to solve it quite quickly. So for example, one thing I could do is, if I said you can only use each block once, that it turns out the problem is in NP pretty easily. And it's actually very similar to problems we've seen before, like along the lines of subset sum. It's not the same as subset sum, but it's the same sort of general class of problem. If I can only use each problem once, or each block once, then really what I'm doing is considering a particular subset of blocks. And there are a finite number of those. In fact, there are just an exponential number of them in terms of the number of blocks n. If I wanted to, I could just iterate over all of them and try all of them. In a more formal sense, I could think of that problem as being in NP because I could just look at a certificate, where a certificate would correspond to a subset of blocks and therefore be polynomial size, and I could validate that in polynomial time. So one thing that I should observe is, when we find problems that are undecidable, basically what's happened is that the computational power of the problem has gotten too great. The post-correspondence problem is complicated enough that it can be used to accomplish impossible tasks, like solving the halting problem. If you want to solve the post-correspondence problem, all you really have to do is weaken it by just enough that it can no longer have that amount of power. As I said, if you limit the number of times you can use each block, for example, if you say you can use each block once, or you can use each block at most 100 times, well, that would be sufficient. And so if you weaken the problem, you often can make it solvable. One pretty easy weakening of the problem here would be, I'm going to add a parameter q. And now I want to ask whether there exists a sequence, so a viable solution, of length at most q. So here I'm putting an upper bound on how long the sequence of blocks can be. And this by itself is enough to make the problem solvable, because I could just test every possible collection of q or fewer combinations of blocks, which might take a long time depending on the value of q and whether, p equals np and whatever. But it would still be something doable in a finite amount of time, very concretely. Like, it's clear that if I'm looking at a finite collection, even a massive finite collection, I can iterate over all of its elements in a finite amount of time and just try all of them. And so you can see, if I weaken the post-correspondence problem the right way, I can find a way of solving it. In fact, I can even solve the halting problem if I add some limitations that weaken it. Now, you're free, if you'd like, to take that out of context and quote me as saying that I can solve the halting problem. I'll look forward to the angry emails I get about that. But if I modify the halting problem by adding the same parameter q, so you give me a Turing machine and some integer q, and now the decision problem becomes true if m halts within q steps and false otherwise. Well, clearly that's solvable. Just run the simulator for q steps. If it halts, the answer is true. If not, the answer is false. Notice how adding that one extra parameter and one restriction turns the problem into something very theoretically strange and impossible into something that's really obviously solvable. Like, we didn't even have to go through a proof that this was solvable. It's very clear I can solve this problem. And that's it. That's the end of the road. This was our course about algorithms. An algorithm is a way of doing something. The purpose of an algorithm describes how to do some task. And we know by now, of course, that the fact that the task is finite is critical. We also have spent lots of time understanding what it means for an algorithm to be efficient. Performing a task with finite resources is one thing. We want to use as few resources as possible. If there are multiple ways to solve a problem, we want the way of choosing a solution that is efficient, that uses as little time as possible, or maybe as little space as possible, or in fact even things like as little power as possible, or even things like as few random bits as possible, as you might see in some future course. We've learned over this course that some problems that seem really complicated can actually be solved by surprisingly elegant and efficient and satisfying algorithms. We've also noticed that there are problems out there that seem relatively simple that require, apparently, as far as we know in August 2025, surprisingly difficult and intractable algorithms. So while we were able to find minimum cost maximum flows using elegant solutions, and it turns out, as you'll see in some future course, that we can in fact do this in polynomial time, the lowly partition problem, as far as we know, does not have a polynomial time solution, or at least none that we've seen so far, even though, as I keep saying, the problem itself doesn't seem that complicated. And finally, we've learned that there actually are some problems I can specify clearly and mathematically that cannot be solved by algorithms at all. Unless, of course, you want to just try solving the problem by trying every combination and potentially wait until eternity to have your solution. Now, frankly, eternity isn't that long. I guess it's frankly about as long as it takes to design an algorithms course.